I hope you can see that. So therefore, n of x inverse is just the same as n of x. We don't need to know the number. We just know intuitively that. So n of x would be. You start with this, give you that, and then x inverse takes you back up again. Well, it's just sort of. It's just going back up the lines in a manner of speaking. So there's the same number of cross points. So n of x inverse equals n of x. All right. So we can rewrite this exponent here this way. Okay. So n of minus x. Oh, sorry. N of x inverse. Sorry. N of x inverse. It's just n of x. Okay, so we now have two of these n of x's here. Now, what's n of a? Well, what is little a here? It's a member of your alternating group. And what's the alternating group? Well, it's the group of all positive permutations. And positive permutations have an n that's even. Right, has an even number of cross points, and therefore it has an even number of transpositions. And the number, whether the number of transpositions of a permutation is even or odd, that's what determines whether the permutation itself is even or odd. Right. So this is even, and 2 times anything. You know, n's an integer. So 2 times anything, that's obviously even, and this is even, so the whole thing is even, right? So n of this is even, and therefore this permutation here belongs to the alternating group. Okay? Therefore, this group here is normal. It's a normal subgroup. Therefore, an is normal, right? So we've proved that. And we proved it was a subgroup in lecture 12, so go back to that. I'm only doing the part we haven't done. So, all right. Okay. Now we're going to. Okay. So we've proved it's a normal subgroup. Now we need to do this second part. Now you just look at that, and you say, oh, well, that's in the form of the first isomorphism theorem, right? Your parent group, the one you start with, slash. Make that a bit. So if that's a kernel, and then this would be your image of f, your mapping f, right? So let's assume, well, it's in chapter 19, right? So obviously this question has some connection with the topic of this chapter, because it's an exercise for the chapter. So let's interpret this as, so this will probably be the kernel, okay? And this will be your image of f, the function, your function. All right, so, so if we're going to pursue that strategy, we need to know what f is. So what are we mapping? Mapping what to what? Well, have a look at this. So we've got like 1 and minus 1. So we have here a group, and this is a group, you know, because here's your set, here's your binary operation, just ordinary multiplication. And we've only got 2 elements in the group, so it's a cyclic group, you know, 2 elements. So the order of the group is 2, that's a prime number, therefore it's a cyclic group. So it's just, this is just C2, right? Cyclic group order 2. And we're just multiplying 1 minus 1, so it's really trivial group. But what's this got to do with the permutation group or symmetric group, right? So what's the connection? So just 2 things. Well, in the context of the symmetric group, what do we know about that group that somehow gives us like 2 things? Well, the obvious thing is even permutations and odd permutations, right? We know they're an equal number of each in our n factorial number of permutations in symmetric group, permutation group. So that's probably the clue, right? So so we're mapping. Let's say we map permutations. So our function would be something like this. Here it is here. So we're probably mapping a permutation into, well, actually onto, strictly speaking, +1 or -1. So if the permutation x, if it's an even permutation, let's map it to +1. Okay? And if it's an odd permutation, let's map it under this f to -1. Right? So here, well, here's it's not intuitively obvious, but here is the heart, the main idea, if you like. Well, I guess maybe that is, but it's certainly one of them. Anyway, it's one of the main ideas for the solution to this problem. Let's map a permutation into +or -1, right? And if it's an even permutation, we want this right-hand side here to be +1, right? And if if x is an odd permutation, we want this right-hand side to be -1. Okay. Well, we were talking about n before. N is the number of cross points in your permutation. So so we want some power of -1. So either even or odd. So so if x is an even permutation, we want this right-hand side to be +1. And if x is an odd permutation, we want this right-hand side to be -1. So in other words, we want this power here, this exponent of -1, to be integers which are either even or odd. Right? So this n of x comes to mind because it's an integer, and it's even when x is an even permutation, and this n of x is odd when x is an odd permutation. So this looks like a good candidate. Right? So this looks pretty smart, and will do the job. That's our hypothesis, right? That this would be the case. This would be our mapping, our f, from could be a very large group, n factorial. Anything factorial quickly gets large as your n of n factorial increases. Okay, so we're mapping. It's very much a many-to-one mapping, right? So we're mapping this large permutation group, symmetric group, to just two elements, +1 or -1. Okay, so this is our hypothesis. So next step, I mean, if we want to prove the isomorphism, first isomorphism, if we want to use the first isomorphism theorem, we need to go through several steps. We need to show that this f is homomorphic, surjective, the usual things. We did it 4 times previous session, went through that process like a mantra. And what else we need to do? We need to find the image of f. We need to find the kernel of f. Right. So firstly, and then once we've got all those things, then we can use the first isomorphism theorem and prove this. So that's the strategy. So quite a bit of reasoning involved. All right. So we need to show f is homomorphic. F is I've just got homom for short. All right. So we need to show f of xy is equal to fx fy. That's the definition of homomorphism. That's the homomorphism criterion. All right. So if we use this is what we think f should be. It has the right properties, we think. Now let's see if this f is homomorphic. Well, by definition, if you've got xy here, you have xy here. So put it in here. Now from theorem 41, n of x minus 1 to power n of xy is minus 1 to the power nx plus ny. Okay, so we can expand this out to nx plus ny. Now these are just in the exponent of, they're just a power of minus 1. So we can factor this out, split it up into this form, minus 1 to the nx times minus 1 to the ny. But minus 1 to the nx is just f of x, okay? And minus 1 to ny is just f of y. Well, there it is. So fy equals f of xy. So f is homomorphic, alright? So we proved it homomorphic. Now, is f surjective? Surjective. That means every element of your codomain gets mapped to. There are no loners. There's no element of your codomain that is not mapped to. Everything is mapped to. Right? Everything has an arrow to it, if you like. It's mapped to from some element in the domain. All right. So what we're mapping to is just 1 or minus, plus 1 or minus 1. Well, the elements of the alternating group, they are all even permutations. So each one of them, it's n of x. N of x here will be even, right? So